Bismillah ar-Rahman Rahim. Today here we are with another fun lecture of the mechanics of materials. The topic that we would start today is the transformations of stress and strain. As we discussed before that stress is neither scalar or vector, rather it is a new quantity which is known as tensor. So the general state of stress, by general state of stress, we mean when the material is loaded in all the directions. When the material is loaded in all three axes, the loading is along x-axis, y-axis, and also z-axis, then we call it the general state of loading or the general state of stress. Then in that case, how to define stress at a point within the material and how many components it should have. As we discussed before that stress is a tensor, it has 9 components, and in order to define stress or strain at a point inside the material and when there is loading in all 3 directions, then the stress at a point within the material, it should have 9 components. And we could express those 9 components, we could write those 9 components in a matrix form. So this is the general state of stress at point Q. So in order to completely define the stress at a point, it would have 9 components. As it is a general state of stress, the loading is along all 3 axes. So you could see that at this point, the point is represented here. We are representing the point by a cube. We have already discussed that as we are talking about a point, and a point has a 0 volume. So we could exaggerate that point into any shape. We could exaggerate into sphere, cube, cuboid, etc. So here we are exaggerating in order to visualize all of the 9 components. So we are exaggerating the point into a shape of a cube. And here you could see the all of the 9 stress components. On this face, 3 components. You see 3 components also on this face. So the cube has 6 faces. So on all these 6 faces, you would see the 3 components of the stress. Collectively, we have 9 components. So the most general state of stress at a point may be represented by 9 components. And the general notation that we use for stress is sigma xx. We use the subscript, and in the subscript you see 2 notations. The first notation, the first subscript represents the direction of normal unit vector of area of surface. So here you see if we are talking about this face or this surface or this area, so to this area this is the normal. This is the unit normal of this area, and the unit normal of this area is along x-axis. So we have to write here x. And if we look at the stress or loading, the loading itself is along x-axis. So you have to write x-axis. So sigma xx actually represents this stress value. And here, if you see here, this area or this surface, the normal is along x-axis, so x, and the force itself or the stress itself is along y-axis. So the second subscript would be y. And why we are using tau here? Because it is a shear stress. It is not perpendicular to the area. It is along the area. So this is the shear component. And this stress component is perpendicular to the surface. So this is the normal stress component. Similarly, this component, if you look at this component, so this is a normal component because it is perpendicular to this face or this surface. And look, if we look at the notations, so the normal of this area is along y-axis. So the first subscript would be y, and the stress and the force, stress or the force itself is along y-axis. So this component would be sigma yy. Similarly, this component is sigma zz because the normal of the area or the face is along z-axis, and the force which is producing the stress, it is also along z-axis. So this would be sigma zz. If you look at this stress component, it is a shear stress component because it is along the surface, it is not perpendicular to the surface. So this is a shear component, and normally the shear stress component is represented by the tau. So first you have to represent this by tau. And if you look at the the area is along z-axis, so z, and the force is along z-axis. Sorry, the normal of this area, the normal of this area is along y-axis, so y, and the force or the stress is along z-axis, so z, so tau y z. So this is actually the notations or representation of the stress. It could have 9 components. If you look here, the components along the diagonal are the normal components, which is sigma xx, sigma yy, sigma zz. Sometimes we skip the second notation because it is already understood that this is sigma xx, sigma yy, or this is sigma zz. So the components in this matrix, the components along the diagonal are normal stress components. However, the components off diagonal, here there are 3 off diagonal components, they are shear components, and these 3 off diagonal components are also shear components. So we have 3 normal components and 6 shear components. We also discussed that the cross shear components are equal. Why they are equal? Because the point within the material, or the material when it is loaded, the particles inside the material, they are not rotating. So they must be in equilibrium. And in order to satisfy that equilibrium, it means that this tau xy, which is applying here, and on the other face it is here. So if they are, if this is counterclockwise, then the cross shear, which is tau yx, this would be in the opposite direction. It would be in the opposite direction, and the magnitude would be the same. The magnitude would be the same. So we have already discussion on that, that the cross shear would be equal. So tau xy must be equal to tau yx. Tau yz must be equal to tau zy, and tau zx must be equal to tau xz. These are cross components. So it means that if we somehow know or calculate these 3 normal components and these 3 shear components, that is tau sigma xx, sigma yy, sigma zz, and tau xy, tau yz, and tau zx, then we would be in the position to know all these 9 components of the stress at a point. And then we would be in the position, and we could say that we completely know the stress at that point Q. So stress and strain are tensors. They are neither scalar nor vector. We had a discussion on that during the initial lectures of the course. So they are not vectors, they are not scalar. Because vector, we know that vector has 3 components. But this quantity, stress and strain, in general case, they have 9 components. So they are not vector, because vectors have 3 components. They have 9 components. So stress is a tensor. Similarly, strain is a tensor. In general case of loading, um, there would be 9 components for stress, and in general state of loading, there would be 9 components for strain. Sometimes some of these components would be 0 for stress and also for strain. It depends upon what? It depends upon the loading. If you have loading along one axis, then we would have only few components would appear. The remaining all would be 0. So it depends, number one, it depends upon loading. If you have uniaxial loading, then this matrix would be of different shape. We would have 0 value components here. Similarly, in case of bidirectional stresses, when we have loading along two axes, then some components will be 0. Similarly, it also depends upon the coordinate frame. It depends upon the coordinate frame. So sometimes we would choose the coordinate frame such that some of these components would become 0. So sometimes they would appear and sometimes they would be 0. So it depends upon loading and the orientation of this coordinate frame. So normally we could represent the stress by this notation matrix, and in most general case we instead of sigmas we write tau for stresses. So in order to further classify the shear stresses from the normal stresses. Similarly, also you could see here that this is the stress tensor. So it would have 9 components, and we would try to find out all these 9 components if we have the loading in all 3 axes. If we have the loading along 2 axes, then we would have uh, uh, less components. As in the beginning, we discussed that stress is such a concept that it depends upon the cutting plane, it depends upon the orientation frame. If you change the orientation frame, the values of the 9 components would change, or the value of the stress would change. It doesn't mean that if you change the coordinate frame and the values changes, it doesn't mean that in the previous coordinate frame the stress was wrong, but actually it is such a concept. The stress and strain is such a concept that it depends upon the cutting plane, it depends upon the coordinate frame. For example, here you could see that we are showing the stress values in general case at a point Q, but we have defined these stress components in which coordinate frame? In X, Y, Z coordinate frame. So these are the stress values in the X, Y, Z coordinate frame. But if we change the orientation of the coordinate frame, and now if the coordinate frame is X prime, Y prime, and Z prime, then the values of all these 9 components would change, and in new frame we would have a new stress matrix, and that stress matrix would be sigma x prime tau x prime y prime tau x prime z prime, and so on. So this stress is correct, the stress values are correct, but in the new coordinate frame. In the previous coordinate frame, we would have the other stress matrix which we have already discussed. The main objective of discussing this slide is that in order to understand that the stress and strain are tensor, it is such a concept that the value of stress and strain depends upon the cutting plane or orientation of the coordinate frame. So if we change the coordinate frame, all these 9 components, the values of all these 9 components would change. So we would have those stress values in the new coordinate frame. Also, if you look here, so at this point O, we have a coordinate frame X, Y, Z, and we have also passed a coordinate frame, or we have rotated this coordinate frame to some angle, and now our new coordinate frame is x prime, y prime, and z prime. To this point O, we could pass infinite number of coordinate frames. What does that mean? If we could pass infinite number of coordinate frames, it means that we would have infinite number of stress values at point Q. We would have infinite number of stress matrices or strain matrices at point Q. So remember that in order to solve stress problems, we could solve it in any frame. But if it is specified to you that you have to solve this problem in this coordinate frame, then you have to solve in that coordinate frame. If it is not specified, you could solve in any coordinate frame which you think that it is easy for you. So remember that at that point you could pass infinite number of coordinate frames. So we would have infinite solutions for the stress or strain at point Q. But principal stresses or principal planes or principal coordinate frames, in all those infinite coordinate frames, there would be one particular coordinate frame where the shear stress values would disappear. All these shear stress values would become zero, and our stress matrix would become like this. We would have only values along the diagonal. It means that we would have only normal components of the stress. Whereas on this stress matrix, the shear stress values would all be zero. So that particular coordinate frame is known as principal coordinate frame. And the particular axes, those particular axes are known as principal axes. And the values of the normal stress at those principal axes are known as principal stresses. They are known as principal stresses. And those principal stresses, normal stresses, would be either maximum or minimum. Some would be maximum and some would be minimum. That would we would be discussing in our coming lectures or coming slides. And we actually, why we need to find those principal stresses? Because we are doing designing on those principal stresses. As I told you that those stresses would be maximum or minimum. So because in order to design a component, we need to find out what are the maximum stresses at which axes the stresses are maximum. So if we know those axes, or if we know the magnitude of those stresses, then it would be very easy for us to design the mechanical components. Before designing, we could easily predict that these would be the planes, these would be the axes along the loading is maximum, the stresses are maximum, the strains are maximum, and these are the most probable axes or planes through which the material could fade. So it is very important to know the orientation of the principal axes and the amount of or magnitude of the principal stresses. So we are actually interested in finding the maximum normal stresses, and also we are interested in finding the maximum shear stresses. What are the planes or what are the axes over which the shear stress is maximum? What are the axes over which the normal stresses are maximum? So the normal stresses would be maximum at the principal axis, and we have to try to find those axes. So we would be using such techniques or methods by which we could try to find out the principal stresses and we would like to find out the maximum shear stresses. So as I told you that the whether those 9 components would be 0 or non-zero, it depends upon the type of loading. It depends on the type of orientation frame, as we discussed that in the principal orientation frame or along the principal axis, the shear components, all shear components would become 0. Similarly, it depends upon the loading. If you look here, we have the stress element, but you could see that the loading, there is no loading along z direction. There is no loading along z direction. So for that, normally we discuss such problems, classify such problems as plane stress problem, plane stress problem. So plane stress, state of stress in which two faces of the cube elements are free of stress. So here you see that this face is free of loading or stress, and the opposite face is free from loading or stress. So this is a pure two-dimensional problem. If you look to the cube in this direction, so we would just see a square, and on that square, you could see this loading, this loading, this loading, this loading, and these shear loading. So this is now a pure two-dimensional problem. In the previous case, when we have a general state of loading, when we have a loading in all three directions, when we have a loading in all directions, then in that case, the problem would be a three-dimensional problem. And in that case, you need to find out all these 9 components. But here, from the beginning, we know that this is the case of two-dimensional stresses, or bidimensional stresses. We classify this as a plane stress problem. So from the beginning, we know that the only sigma x is there, that is sigma xx, sigma yy is there, and tau xy, and cross shear tau yx, it is there. So we have only 4 components will be non-zero, whereas all the remaining 5 components would be 0. So we would have sigma x, sigma y, tau xy, tau yx, and the remaining components which are associated with the z-axis, they would all be 0. So sigma z would be 0. Where z appears, all those components would be 0. So in that case, we would have this stress component or stress matrix. Similarly, here you could see that this is a thin sheet, and you could see the loading along the thin sheet. So there is no loading on this face or this surface. The loading is only along these faces or these surfaces. So actually, this is the problem of 2D stresses or plane stress. This is the plane stress problem. So state of plane stress occurs when a thin plate subjected to forces acting in the mid plane of the plate. So you could see that loading is along this axis, and the loading is along this axis. Along the third axis, there is no loading. So this is the problem of plane stress, or this is also the example of a plane stress biaxial biaxial stresses problem. Similarly, here you could see that the loading is on this face. This surface, there is no loading. So on this surface, if you are solving the problem for this surface, so this is a plane stress problem. So state of plane stress also occurs on the free surface of a structure element or machine component, that is, at any point of the surface not subjected to an external force. The force is on the component, but the force is acting on this space or surface of the mechanical component. So here we would have, there is a possibility that we would have a triaxial stress problem, but this surface is free of loading. So here we would have a plane stress problem. With